Okay, we just finished a section about infinite limits, which was as I approach x equals 2, or any given x value, my y value goes to infinity or negative infinity. So the function goes up towards infinity, and the function goes down towards negative infinity, potentially. Grows without bound, decreases without bound. Now we're going to look at limits at infinity. Notice this is not infinite limits, this is limits at infinity. So instead of going up and down, what we're going to look at is what happens to my function as I go all the way to the left and all the way to the right. So instead of x approaching a number like x equals 5, we're actually going to be looking at what happens at the ends of the graph. As x approaches infinity would be the right end behavior, and as x approaches negative infinity would be the left end behavior. Notice when it went up and down, when the graph grew without bound or decreased without bound, that created a vertical asymptote. So that's as we go up and down, which is our y values, right? Well, now we're going to be going left and right. And so these are not going to be vertical asymptotes, which is what we saw in the last section. These are actually going to be horizontal asymptotes. Remember, vertical asymptotes in the last section were x equals. These are horizontal asymptotes, so we're going to have to write our answers as y equals. So let's go ahead and take a look at this. It says limits at infinity. It says this section discusses the end behavior of a function on an infinite interval. Consider the graph of f of x equals 3x squared all over x squared plus 1, as shown in figure 4.32. Graphically, you can see that f of x appears to approach 3, so the y value approaches 3 as x increases or decreases without bound. So as I go all the way to the right and all the way to the left, my y value of this function, as I go to the right, notice the y value approaches 3. As I go to the left, the y value approaches 3. Okay? It says you can come to the same conclusion numerically as shown in the table. So we are able to use a table on this one, but this table is very, very different than anything we've done. Notice, look, as I go to the right of 0, my x values go from 1, 10, 100. So I'm getting larger by scale, a scale of 10 each time. And look at my y values. I notice my y values are getting closer and closer to the number 3, okay? As I go to the left, I plug in -1, -10, -100. Look at what's happening to my y values. My y values, again, are getting closer and closer to the number 3. So my x is the one growing without bound. My x is the one decreasing without bound. My y is the value that's actually stabilizing now, okay? So it says, the table suggests that f of x approaches 3 as x increases without bound, which is x approaches infinity. And it says similarly, f of x approaches 3 as x decreases without bound, x approaching negative infinity. These limits at infinity are denoted by, and so notice now the infinity and negative infinity belong for the x value. Okay, so we're plugging in infinity and negative infinity for the x value. Again, you can't plug in infinity. It's just saying what happens as these numbers get bigger and bigger. And you can't plug in negative infinity. You just plug in smaller and smaller negative numbers. And then notice our y value stabilized at 3. It says the statement limit as x approaches negative infinity of f of x equals L, or limit as x approaches infinity of f of x equals L, means that the limit exists and the limit is equal to L. So when we had vertical, when it went up towards infinity, growing without bound, and it went down towards negative infinity, decreasing without bound, technically those limits didn't exist because they don't equal a single number. All we were doing was saying equals infinity or equals negative infinity because what we were saying is this is the behavior of the graph. But here we are physically saying the limit exists. It approaches a single value. So these ones, limits at infinity, exist. The previous section, infinite limits, did not exist.